So we are doing the shell method. It is based on surface area. When we do this, we are going to use 2 pi r times the height. So if you think about like finding a cylinder's area, you would say 2 pi r, that's the circumference times the height. So that would give you kind of that shell. And then if you take all of the shells together, that would give you the volume. And so that's where the integration piece comes from. The formula for that is right below it, or on the top of the next page rather. It depends on which way you rotate it, all right? If you have a horizontal axis of revolution, so we are revolving around the x-axis or something parallel to the x-axis, then all of your stuff needs to be in terms of y, all right? So if we are revolving horizontally, then things need to be in terms of y. If we are revolving vertically, vertical axis of revolution, then our functions need to be in terms of x, all right? So if we are revolving around the x-axis, our functions will be x equals something, all right? If we're revolving around the x-axis, then our functions will be x equals y. So all of this in here will be y. So these are the two you need to remember, and they are opposite of the disc washer method. They're opposite of the disc washer method, all right? Let's look at just doing one the way it is. It says find the volume of the solid of revolution formed by revolving the region bounded by y equals x minus x cubed. And the x-axis, 0 is less than or equal to x, which is less than or equal to y. So those are my boundaries. And we are revolving all of this around the y-axis. So if we are revolving around the y-axis, my function needs to be in terms of y equals, and my boundaries are going to follow the variable here as well. So if this function has my x's, my boundaries will be with my x's as well. Okay, the boundaries will always follow what's here. All right, boundaries will always follow these guys. So they've really given me everything that I need. They've given me my upper and lower bounds, 0 to 1. I'm going to have my 2 pi out here. My R is going to be, so I'm revolving around this right here, this axis. My radius, or my R, is going to be the horizontal distance to this center piece here. That is just going to be x. From my y-axis to here is just going to be the value of x, okay? Right? If I'm at 1, that's 1 away. If I'm at 2, that's 2 away. It's just the value of x. So x is going to be that piece of it, my r. My height changes. It changes with my function. So my height here is something different than my height over here. So my height will follow my function. So this next piece is just going to be my function, what they gave me. X minus x cubed dx. And that is the whole setup here. Now keep in mind, with the disk method, if I were doing this with the disk method, I would have to rewrite this in terms of x equals something. That's not something I want to do, right? Mm-hmm. I don't want to get x by itself. I don't know if I could get x by itself. I would get x and x squared minus 1 there, or 1 minus x squared, like, no. So I would not rewrite this. I would use the shell method, okay? And so with this one, we actually have a rather simple distribute. We have x squared minus x to the 4th. Take my antiderivative, 2 pi. That x squared is going to become x cubed, 1/3 x cubed. Minus, this is going to be 1/5 x to the 5th. And we are going from 0 to 1. I end up with 2 pi. 1/3 minus 1/5. My common denominator is 15, so I have 5/15 minus 3/15, which is 2/15 times 2 pi, which is 4 pi over 15. And I am done. So I have x equals e to the negative y squared. They've given me my upper and lower bound. They've given me what I'm revolving around, x-axis. Since it is x-axis, I need x equals. I have it. Don't rewrite it. Use the shell method, okay? And so shell method said 2 pi. My upper and lower is 0 to 1. What is my r this time? Well, if I'm revolving around the x-axis, my r, p of y, which represents the r, is just the distance from the x-axis. I measure the distance from the x-axis by my y value. So that's what I'm going to use. Y times my function, e to the negative y squared, dy. All right? You do want to use substitution here. You want to think about what you're missing and what you have. So if I were to do u equals my negative y squared, my du here would be negative 2y dy. I have a 2 and I have a y. You just have to consider that you're going to have a negative in your answer, right? That negative is what's going to affect your answer. So you don't have to necessarily do u substitution. You just have to consider the antiderivative of e is just e, but I do have to think about my exponent. My exponent generates a negative, all right? And because I generate a negative here, I have to consider the negative in my final answer. I also don't have to worry about that 2. So if I rewrite this using that u substitution, 0 to 1, I still have that pi, okay? I have e to the u, that takes care of this guy, right? And du takes care of the 2 and the dy. I just need to put that negative in place. So that's what the new one looks like when I do u substitution here.
Where did 2 go?
So antiderivative of e to the u is just e to the u, right? That is my antiderivative there. Negative pi times e to the u. Remember, with u substitution, I have to go back in and redo that, or I can plug in my boundaries here if I want to, okay? Whichever one you want to do. So when I plug it back in, I'm going to get negative pi times e to the negative y squared from 0 to 1, right? I actually end up, so think about substitution when I plug it in here. I have negative pi, you can just leave them out there. When I plug in a 1 here, I get e to the negative 1. When I plug in a 0, I get e to the 0. What is e to the 0?
So, 1.
It's 1. Yes. Don't put 0 there. It's 1. All right, and I think they distributed that negative through. They rewrote it. They had 1 minus 1 over e. But you're going to put this into your calculator anyway because it's e to a power, and you're going to get approximately 1.986 there. So this is comparing your disk versus your shell. The first two are disk method, all right? The disk method is pi r squared. When you have a whole, you're going to do r squared minus r squared. When you're revolving around, when you have two functions and you're revolving around something butted right up next to it, you're just going to subtract the r's first and then square them. But either way, this is the disk method, whether there's a whole or not, it's the same method. Pay attention to the revolution. When I'm revolving vertically, I need to be in terms of y for the disk. When I'm revolving horizontally, I need to be in terms of x. This is disk method. For shell, when I'm revolving vertically, I need to be in terms of x. When I'm revolving horizontally, I need to be in terms of y. Okay? So they are opposite. You need to come up with a method of memorization, pretty much. Okay? So if you're subtracting the r's, then it's going to follow the axis, really. The y-axis is the y, the x-axis is the x, okay? When you're doing 2 pi r, the y-axis is in terms of x, and the x-axis is in terms of y, okay? So you've got to remember that they flip-flop. When you do pi r squared, y-axis in terms of y, x-axis in terms of x. When you're doing the 2 pi r, y-axis is in terms of x, x-axis is in terms of y.
So we had,
We actually did this exact example with the disk method. Okay, when we did this example with the disk method, we actually did 2 revolutions. All right, because we did the first one that created this little box here that revolved without a gap, and then we did a second revolution with this part that created a gap. Okay, so we had 2 different ones. We did from here to 1, and then from here we did the function. When we have shell method, we can do it just one time. We don't have to do it both ways. So it says find the volume of the solid by revolving the region bounded by these graphs around the y-axis. All right, so it's around the y-axis. In this case, we can just think about this. And now we're going to revolve this guy right here one time. We're not going to have to do 2 separate ones because before we had a gap and no gap. We had to do a disk and a washer because we ended up with no gap up to here and a gap from here forward when we did the other way. We don't have to worry about this for this one. We are revolving around the y-axis, which means we need the dependent variable to be x. All right, so we are doing a vertical revolution, y-axis, which means I need this in terms of x, which is how it's written already. I'm good to go with that. Before we had to rewrite it. So before we had to move the 1 over and take the square root of both sides. That's what we did when we did the disk method. We don't have to rewrite it this time, nor do we have to do 2 revolutions. We can just do 1. And so we have our boundaries. Our boundaries should be in terms of x, 0 to 1. So that's what I'm going to go from, 0 to 1. I'm going to say 2 pi r. My r is going to be my distance of my x. So my r here is just the x. My function or my height here is going to be the function the way it's written. I do not have to rewrite this one using the shell method. I rewrote it last time. I don't have to. So this method, shell method, is way easier for this function than the disk method was. If you look in your book, the very first solution to this was what we did in section 1 for this exact problem. Do you see that huge solution? That's what we did in section 1, that first solution there in your book on the top of this page. So we had to set up 2 separate revolutions for this, one with a gap, one without a gap. All right? This shell method for this particular function is way easier. We do not have to rewrite. We do not have to set up 2 separate integrations. One integration here. Distribute your x. You have x cubed plus x. That's a really easy antiderivative. It's going to be 2 pi. We're going to say 1/4 x to the 4th plus 1/2 x squared. We are going from 0 to 1. So we end up with 1/4 plus 1/2. That gives me 3 halves, right? 3/4 times 2 pi. 3/4 times 2 pi. That's going to give me 3/2 pi. Which is exactly what you get if you do the disk method. If you notice the solution above this in your book, that long solution, when we set up 2 revolutions, we got 3/2 pi. And so this is the exact example that we did in the disk method. We just used a different method. So the 2 methods will give you the same volume every single time. Same volume. It just depends on which makes your life easier. In the disk method, I had to rewrite it to square root of y minus 1. And then I had to do 2 revolutions. Because with a disk, I have no gap here, I have a gap here. And it needed to be rewritten for my variables. With shell method, I don't have to worry about that. 2 pi r, it's already in the terms that I needed to be in. Much, much easier to do shell method for this one. Much less room for error with this one.